Okay, so we're going to look at fossil fuel resources more specifically now. We're going to get into things that range from coal all the way up to like natural gas. We're also going to look at the other non-renewable nuclear stuff later on. So we're going to look at the pros and cons of coal, look at the pros and cons of petroleum, natural gas, and things like oil sands and CTL or CLT, liquefied coal, and what's going to happen in the future as we expend these resources. All right, so what is coal? Okay, solid fuel formed primarily from the remains of trees, ferns, and other plants. What you need to know is that this comes from plants. So when you think coal, you need to think plants. Okay, plants. All right, and here's the timeline. Because remember we said in the first 12A, we were talking about there's a differentiation of all the fossil fuels in terms of the organic sources and also the amount of time that it takes. So between 280 and 360 million years ago, this is a very slow process to fossilize these plants. Coal can be divided up into 4 different types. We have lignite, subbituminous, bituminous, and anthracite. This one right here is the most energy dense right here. There's also peat, and peat's going to be more like one of these. Okay, peat. So peat is a mix of a little bit of coal with some partially decayed organic. All right, here we go. Here's peat. So you can see that it's not very far along in terms of decomposition and fossilization. In aerobic conditions, forming of peat, partially decomposed organic matter. All right, here then you have the lignite. So this is in millions of years. This layer of peat is buried deeper. It's compressed into lignite. So this really has to do with exposure to pressure and temperature over a long period of time. So bituminous coal. So the lignite layers are buried even deeper. Increased pressure compresses it into soft bituminous coal. And then here you have from hundreds of millions to 280 to 360 million years, you have anthracite. Okay, this is really high pressure tectonic activity and heat transforming bituminous coal into harder anthracite coal. Okay, so here's the coal formation process. So you probably want to know this graph right here and kind of just show the differentiation on your own so that way you can study. Here are the advantages of coal. It's very energy dense. It's plentiful. We have more of this probably than anything else at the moment. It's easy to exploit from surface mining, and that's important because right here we talked earlier about the energy input to the energy output, right? So the return on energy input versus the energy output, right? Since we're just surface mining, we're not really having to drill, we're not having to bring a bunch of extra water like we would with like fracking or something. So the carbon footprint for this is relatively small in the beginning, right? Because we're not really having to do a whole lot because it's right at the surface. So we don't need very much refining, so that's also going to decrease the energy requirements. It's inexpensive. It's easy to handle and transport. Nobody's going to, blow up just from touching this. Although there are negative health effects from breathing this stuff, and you get like the black lung. There have been coal mines that do collapse, and you can have fires in these mines, which are very deadly. All right, disadvantages of coal: it contains impurities. So like sulfurs. That's what we're talking about here. Your socks, right? Releases impurities into the air when burned. And that's going to be sulfurs, and it's going to get acid rain from that. You can have trace metals like mercury, lead, and arsenic. So these are things you want to know because on your AP exam, sometimes FRQs will ask, other than carbon dioxide, other than sulfates, or sulfuric acids and things like that, what are some other elements that can be released into the environment, and what are the effects? So you want to be able to list these as well. Our combustion of coal leads to increased pollutants, such as CO2 and things like that. And ash is left behind. The ash is a contaminant as well. And there have been instances when containment fields that hold the ash from coal refining facilities, they end up breaking down, and they have these big, gigantic ash floods, and it causes lots of damage to the environment, and people have to evacuate. So, as with everything, if you relate this to the hydrologic cycle, it's going to lead to runoff. Okay, runoff is a bad thing because it can affect ecosystems negatively. So coal. All right, petroleum. Petroleum is slightly cleaner than coal. When we say things like clean coal and clean natural gas, we just mean relative to the thing that came before. Coal is going to be the dirtiest, right? Petroleum is a little bit cleaner just because it has less impurities, but it's not better, or it's not good for the environment just because it's a little cleaner. Okay, so what is petroleum? It's a fossil fuel that occurs from liquid hydrocarbons, water, and sulfur. And it's going to come from this one. This one should come from phytoplankton, right? So crude oil is liquid petroleum removed from the ground. And petroleum, since it is like a liquid oil, it's going to migrate upward because it's less dense. It's going to come out of this shale, or it's going to leach out of there. Okay, petroleum migrates to the highest point in the formation of the porous rock. Remember, if it's not porous, if it's impermeable, then it's not going to be able to do that. Right, these accumulations can be removed from drilling a well. It's going to move very, very similarly to how artisanal wells work. Right, so this is very similar to how an artisanal well operates. All right, what are the advantages of petroleum? All right, they're convenient to transport and use because it's a liquid. Right, liquids. What do liquids do? Right, you remember this from all of your science classes. Liquids take the shape of their containers. Right. Yeah, so it's very easy. It's also very easy to compress because it's a liquid, right? It's relatively energy dense, and it's cleaner burning than coal, and it's used in many other applications, such as industrial uses like forming plastics, lubricants, things like that. Disadvantages of petroleum: it releases carbon dioxide in the atmosphere. We're very, very well aware of that. Leaks when extracted and transported, so like pipelines and oil source facilities where there's drilling. You know some pretty famous ones like British Petroleum, right? The BP, the Deepwater Horizon. The runoff is always an issue. Okay, and again, here's sulfur, mercury, lead, and arsenic. So these are the ones you want to know right here. Always relate any sort of impurities to these four right here. But what is really nice about petroleum, if we go back to the advantages real quick, is if you form it into like gasoline. It's something that you would prefer to fuel your car with over something like coal, right? You could use coal, but it's very slow to burn, and you need to be able to use really high amounts of energy in short time periods and be able to stop the burn immediately by turning off your car's engine, right? Now, if you have a coal fire, it's a little bit harder to put that out and start it up. So it's not necessarily something that has a lot of ready energy that could be used quickly. So it has a lot of energy per liter, and that's the nice thing about petroleum and gasoline. And now let's talk some more about the disadvantages. Now you need to know this acronym ANWR. This is Arctic National Wildlife Refuge. There are some debates over the trade-off between extracting oil domestically and getting it from somewhere else. And a really big source that we could potentially use would be the Arctic, right? And the problem with that is that it is a habitat for species, so we'd be practicing habitat destruction. Also, by moving the permafrost off, you're going to expose a lot of organic material, right? So the permafrost has a lot of organic material underneath it, dead organic material. And what happens when you release a bunch of dead organic material? Well, they release a lot of greenhouse gases, CH4, methane, right? Methane, as we know, is very, very potent greenhouse gas. So even though we could yield up to 25 million gallons or 378 billion gallons of oil, the substantial qualities of gas, it can, destroy the habitat and speed up climate change. Our natural gas is the cleanest of the fossil fuels, but it still lets out pretty potent greenhouse gases in addition to CO2. Natural gas exists as a component of petroleum, as well as in gaseous deposits that separate from petroleum. Natural gas contains 80 to 95% methane and 5 to 20% ethane, propane, and butane. So this is the key right here. Methane, as we know, can be up to somewhere between 25 to 27 times more powerful as a greenhouse gas as CO2. Right now we're using it for electricity generation, not so much in cars or anything like that, right? And industrial processes. Natural gas can also be used to manufacture nitrogen-based fertilizers. If you liquefy natural gas, you can use it as a fuel, especially propane. That's how a lot of our buses are powered, or at least a mixture of this. Right. The nice things about natural gas that it has fewer impurities, so it's going to have almost no sulfur dioxide, or particulates. It only has about 65% as much carbon dioxide as coal, and petroleum had about 80%, so that's still lower. But you can see that's what they mean by clean. It's that it has a little bit less, quite a bit less, but it's still not clean, as in it's not having any foot whatsoever. All right, so here are some disadvantages. Methane, as we talked about before, is a very potent greenhouse gas. and it can contaminate groundwater. So all of these things can contaminate groundwater. You need to know that. All right, here's some other sources of fossil fuels and the different arrangements that we can find them. Here's oil sands, slow-flowing viscous, which means like kind of sticky, like almost like jelly or something. Deposits of bitumen mixed with sand, water, and clay. And the process of removing the oil from this kind of mixture can be energy intensive, but it is something that we're looking into. Right now, when we use the processes to remove oil from these oils, so these tar sands, oil sands, sometimes it takes about 2/3 of the energy we get out of it. So it's a much lower return on energy input, right? Bitumen, a degraded petroleum that forms when petroleum migrates to the surface of Earth and is modified by bacteria. And coal to liquid, process of converting solid coal into liquid fuel. The Germans did this in World War II to power some of their machines. It's very, very dirty. It's very dirty, but it might be something we look at as we start running out of petroleum, because we have so much coal. Fossil fuels are a finite resource. So they're finite. We don't have them forever. We don't quite know exactly when we'll run out of them, but some of the most dangerous estimates, or the least conservative estimates, say that we should be out of things like petroleum within the next 50 years, maybe longer, right? It just depends on what sources are still out there. But you really do have to weigh this with the problems of, not just abundance. So should we figure something out before the abundance is gone? Or should we do something about it because it is perhaps having a very large, not perhaps, it's having a really large effect on the climate. So which one of these should be motivating us more to find an alternate energy source? Should it be because we're running out, or should it be climate, or should it be both? Which one of these do you think we should care about more? Okay, energy intensity. The energy used per unit of gross domestic product. Now this is kind of a really wordy thing here, but think about this, the amount of money we're making. So if we're saying that we have a low energy intensity, that means the amount of energy we're using is low, but we could be making a lot of money. Okay, so we'll look at a graph right now to kind of see what the trend is in the United States. Do you think in the most recent years that we've been using a lot of energy to make our money, or have we been decreasing the energy intensity? So let's look at that in a second. And actually, here's the answer. I should have read the whole PowerPoint. Okay, our energy intensity, or energy use per capita, has been dropping, but since we have more people, our total energy numbers continue to rise. And what are some things that we do as individuals in the modern age, as like millennials or Generation X? What are some things we do now that would use more energy than the generations before us? Well, if you have any relatives that maybe lived out in the sticks, that they only had light during the day and no light at night, we definitely have a much higher number of electronics per person. You go home, you might have like 5 or 6 things plugged in at a time when you're doing your homework. You might have your phone plugged in, your laptop plugged in. You might have a clock radio. You might have a hamburger radio. You might have a microwave radio, a bird alarm clock. You might have all these things plugged in. Your grandparents might not have had any of those things. Maybe a transistor radio, a toaster. All right, so here's that graph I was talking about. Here's our energy use per capita, the energy intensity. You can see that it was going up for a while in the 50s and 60s, a lot of manufacturing here. But now we are starting to figure out more efficient ways to produce things, or maybe we're not producing as many things, right? Per GDP. Maybe it's because a lot of our GDP is produced by services now, and maybe not so much manufacturing. So here's our energy use per dollar GDP. This is going down big time, but we are still using quite a bit of energy because we have so many electronics, and we have a large number of people that use electronics. Whether you're rich or poor, you probably have a phone, right? And so that matters. You probably have a TV, 1 or 2 of them, because the technology to get a TV isn't that expensive anymore. Okay, the Hubbert curve. What is the Hubbert curve? Basically, the Hubbert curve says whether we have a lot more fossil fuels than I thought, or the least amount of fossil fuels left in the world. We are going to peak at about halfway through the use of all of our fossil fuels. So the rate of use of the fossil fuels is going to peak at around when we use about half of it up. Then the use of it's going to come down. All right, we're going to stop producing as much. But either way, whether we have this much oil or this much oil, the time in which we're going to run out should be about the same. So that's not a good thing, or maybe it is a good thing. But all I know is that when we get here, if our population size is still the same, we're going to have almost the same energy requirements. We're going to need the same number of resources to keep our carrying capacity where it's at, right? So I have this debate with people a lot about whether we should be concerned about food production and GMOs and all that in terms of carrying capacity and what size population can be supported on the planet. Everybody's always like, oh, we'll develop technology and we'll make these super crops and we can vertically garden. Yeah, but that's not the only limiting factor, right? Those aren't the only limiting factors you got to worry about, right? So limiting factors that we've talked about in the past could be food, right? Could be access to water. Could be housing. But what we really also need to be talking about is energy as well, right? Or energy requirements to carry out daily functions, to carry out things like transportation, to carry out heating and cooling, right? If you live in Canada and we run out of energy, it might not be survivable for a lot of people. We might have to go back to subsistence energy gathering, burning wood and coal in our houses, and those indoor pollutants have a big effect on us, right? These are things you can't really ignore. So you have to take into account that whether we have an abundance of these materials or not, and how long they're going to last. Something's going to happen to our population here if we don't have a replacement. So it's probably a good idea to have a backup soon. The future of fossil fuels. 50 years will probably run out of conventional oil. Coal supplies at least 200 years, and probably much longer. We have a lot of coal. New technology and concern about the release of greenhouse gases is encouraging to people to explore alternative energy sources. I hope so, right? I hope so. There are a lot of moneyed powers or invested interests in keeping these businesses running, right, for hundreds of years to the foreseeable future, right? It's hard for human beings who are very risk averse and very short-term gain species, right? That's in our genetics, right? To try to gain as much as we can in the short term and not really worry about what's happening tomorrow. It's hard for us to have sight of the future, especially when human life expectancies are 70 and 80, right? It's hard to, if we only live to 70 years old, it's very easy and lazy, but still easy to say, well, 200 years, I don't even care. And for people that are middle-aged, I don't even really care in 50 years. You guys figure it out. But it's up to all of us, I think, to explore alternative energy resources, to fund them, even if they don't always work, and to support them. All right, let's talk about nuclear energy real quick. We're going to learn how it's used to generate electricity, and surprisingly, it's not too different than what we're doing with thermal energy plants with coal. We're going to look at the advantages and disadvantages of nuclear energy. All right, so we use uranium-235 as a fuel source. You don't have very much uranium-235 when you go uranium mining. You get a lot of uranium-238, which is a little bit heavier isotope, and you have to kind of chemically enrich that to get it down to 235, and that's very energy intensive. So within a good sample, you might get 3% uranium-235, and the rest will be 238. So that's just kind of like some background inside baseball there. It's worth noting that all of our nuclear power so far has been from fission. That's breaking apart a large atomic nucleus by shooting neutrons at a large uranium-235 isotope. When it does that, it's going to break down. It's going to split that atom up into smaller parent and daughter nuclei, like plutonium, things like that. And then the neutrons that are split from that are going to run into other things, and it's going to create like a chain fission reaction. So that's kind of nice. That heat generated from the nuclear fission boils water. This should look very familiar. It's going to produce steam to turn a turbine, which then turns a generator. So this is essentially the same design. After, instead of burning coal, you are, fissiling things. You're breaking them apart, right? All right, so here's a picture of that. You see here are the smaller nuclei. You see smaller nuclei still, and then the neutrons that are left over collide with other things, and they make them break up. Yeah. Nuclear reactors use fission to generate electricity. So here are some components of it. A fuel rod, cylindrical tube that encloses nuclear fuel in a reactor. So you have all these 238, they break them down into like little pellets, and they'll put them into these cylindrical tubes within tubes. And that'll be where the nuclei collide. Now a control rod is another cylindrical device inserted between fuel rods to absorb excess neutron to slow or stop the fission reaction. Because what will happen in a lot of like these nuclear accidents we're going to learn about is something happens to either the control rod or like the cooling tanks or something, usually human error, and these neutrons will have these runaway chain reactions. There's nothing to slow down the rate at which the reactions are happening, so it'll overheat. So the heat, remember that heat in physics is Q. You'll have too much heat, right? The heat goes way up, and what do you get? You end up melting control rods. And what do we call that? This is called a meltdown. Yeah, so that's where a meltdown comes from. It's really not that fantastic, is it? So here are the advantages. You don't get any air pollution when you're actually producing electricity during electricity production. Let's see if I can spell this one right. This is not to say that when you are mining the materials, okay, so not when you're mining. When you are mining, you are leaving behind some sort of footprint, right? So you don't get air pollution when you're actually running the nuclear power plant, but when you're mining for uranium, when you're moving the trucks around to actually move the material, mining, transportation, see if I spell transport right in this one. When you are transporting the materials, you do have CO2 emissions, but that pales in comparison to, a coal factory or something like that, right? Okay, it reduces the need to import oil. I mean, that's obvious. If we have an alternate source of energy, we wouldn't be using oil necessarily, right? Here's some disadvantages. These are some big ones, right? This is that small little 2% that means a whole lot, right? The possibility of accidents. There are 3 well-documented cases that I want you guys to study. We'll watch a documentary on one of them. But when there are accidents that happen, and luckily they haven't been as catastrophic as you could imagine. It's not like an atomic bomb going up. But the nuclear fallout, the drift of the material in the air, has some long-term health effects. So these accidents are very, very hard to clean up. They're very expensive as well. It's difficult to dispose of waste because we're going to talk about half-life in a minute. Not the game, but we're going to talk about half-life of the material and how long it takes for these materials to degrade into safe radioactive quantities, right? So we're going to talk about it. Okay, so radioactive waste, why is it so hard to clean up? Okay, the nuclear fuel that can no longer produce enough heat to be useful takes more energy to break it down than you would actually get out of it. It still emits radioactivity, right? It's breaking down, it's doing nuclear decay. If you're in chemistry, you'll probably be learning about nuclear decay soon. When you break down stuff, you release beta rays, gamma rays sometimes, alpha particles. These things can interact with your genetics, your genes in adverse ways, right? It can make you very sick. Okay, here is a unit of activity. It's called a becquerel or a curie. You need to know that. We're going to practice some mathematics with radioactive waste and radioactive decay. So these spent fuel rods, have radioactive waste, right? They're not going to produce enough heat to boil the water, but they still are going to decay and degrade into smaller and smaller isotopes. Okay. Low-level radioactive waste is found in protective clothing, tools, rags, and other items for people that work in the plant. So it's gonna get coated in like radioactive material. Uranium mine tailings, the residue left after uranium ore is mined and enriched. So these are the 3 types of radioactive waste. This is the one we usually like to focus on because it is the most problematic, right? So this is high-level radioactive waste. And why is this high radioactive waste? Why and this is not? Well, because this guy right here is the source for these 2, right? This thing right here is only radioactive because of the fuel rods. Let's go back a little bit. Okay, so I talked about the previous slide, like why is it so hard? Why is it difficult why are we so concerned with radioactive waste? Because with uranium-235, sometimes it'll take like 7 half-lives. I think that's right. Let me check that again, just a second. It could take 7 half-lives. All right, double check that. It is about 10 half-lives. Yeah, no, not 7, but 10 half-lives. And each half-life can take about 704 million years. 704 million years. So that is a very, very, very long time. And so for our intents and purposes, it is never going to be safe to have this radioactive waste around. So what do we do with it, right? So usually what ends up happening is we put it in the water. Go ahead and put it inside like a containment vessel and place it in water at the same facility. But when you run out of space, so when you don't have enough space to have this water, what you end up having to do is you put it inside a lead container. Remember, lead is PB, lowercase b. All right, PB. and then you just place it on the surface somewhere. And we were thinking about doing this in the Yucca Mountains, but there are a lot of protests because who wants to have this in their backyard, right? Nobody. Okay. All right. Fusion power. Nuclear fusion is what happens inside the sun and other stars. It's when it's the opposite of fission. Instead of breaking things up, you're combining lighter elements. Instead of breaking down a heavy element, you're combining lighter elements like hydrogen. It's very, very difficult to do this. Okay, you need an incredible amount of energy. So we've accomplished nuclear fusion on Earth in labs, but it's not on any appreciable scale that can be useful for generation of power and energy right now. And nowhere near the quantities, and it's not self-sustaining. We can't even get like a chain fusion reaction going on Earth. It takes, you would need something that's 10 times hotter than the center of the sun. Okay, so you want to know this table here. Here's some advantages and disadvantages here. This is in your textbook, but you can get a lot out of just looking at this here. All right, good job, guys.